My name is Yossi Weizman. I'm a principal security researcher at Microsoft. Michael Kaczynski is my partner in this research. Unfortunately, Michael couldn't attend, so I will represent both of us. And this is the agenda for today. We will talk about default misconfigurations. So we will start with an overview of default misconfigurations. Then we will talk about a real-world incident that actually started our entire research. Then we will talk about how did we identify misconfigurations in large scale by using scanner we developed. Then we will talk about containerized AI applications, and we will share statistics, and we will talk about how can we secure our environments from this type of risks. Okay, so let's start. So let's start by talking about misconfigurations. So in the past, many cloud-native applications weren't very secured by default. And in general, security wasn't always a first priority. And let's see some examples that maybe some of you are familiar with. So first, the first example is Helm. As many of you know, in its earlier versions, Helm came with a server-side component called Tiller. This component had permissive cluster-wide permissions in order to manage the deployments in the cluster. And Tiller didn't enforce authentication. So any pod in the cluster could talk to it. So if an attacker got even a limited access to the cluster, they could leverage Tiller to get full control. It was a serious security risk, and that's why in the later versions, Tiller was removed and Helm was changed. Another example is the old Kubernetes dashboard, which was a web interface to manage the cluster. Depends on the exact version, there were several. Sometimes it came without authentication. Also, in this case, once you had initial access in the cluster, you could use the dashboard for privilege escalation. And in some cases, users even exposed the dashboard to the internet, which really helped to the attackers in those cases. And the last example is Kubeflow, which is a very popular framework for building ML pipelines in Kubernetes. And here also, in the past, installations of this framework didn't include built-in authentication. And we saw quite many instances of Kubeflow back then that were exposed to the internet without authentication and were quickly exploited, including in a very large-scale campaign that we observed. And what's common to all of those applications was that, from one hand, they operated with very high privileges, but on the other hand, they did not offer built-in authentication, and that's why workload owners were basically only one mistake from being compromised. And here are some screenshots of blogs and reports of active attacks that originate in misconfigurations. Now, cloud-native applications became more secure over time. There is no doubt about it. The example that we just saw don't really apply anymore. But apparently that such issues still exist. And what if I told you that you can still find even more severe cases, applications that are completely exploitable even with no mistake from the user side, workloads that can be exploited just by installing them with the default settings? And this is our focus for today. Cloud-native applications that are misconfigured out of the box. Okay, so let's talk very briefly about Helm charts defaults. I assume that all of you are familiar with Helm, the package manager in Kubernetes. And what's important for us for this session is that Helm charts come with default values, which are the default settings of the deployment that the maintainer configured. If you don't override it, that's going to be the configuration of your workloads. It's in the values.yaml file. And sometimes, as we are going to see, these default values have surprises. Okay, so let's see real-world examples, right? So just before we talk about our first finding, let's take a second to ask, what turns a misconfiguration into an exploitable misconfiguration? Because there are many misconfigurations, but what turns a misconfiguration into an exploitable one? Usually it's a combination of two things. The first is internet exposure, and very weak authentication or no authentication at all. Or, as we just saw in the news recently, misconfigurations are basically everywhere. So now let's move on to the first finding. Okay. So we'll talk about Apache Pinot. In late 2024, we identified suspicious network activity on multiple Kubernetes clusters. The activity was in the same time. It was identical activity, so we understood that there is a connection between the clusters. And we found that they are all running Apache Pinot. Apache Pinot is a data store that is used for low latency analytics and for querying in real time. Okay, we said interesting. We dived into it, and what we saw is that all of those clusters expose the controller of Apache Pinot externally by a load balancer. So the controller is the main brain of the framework. It handles tables, schema, and the overall orchestration. And it makes sense that if someone got access to the controller, they can take full control over the application. But the question is, why so many clusters expose it? And even if it's exposed, how malicious actors can take advantage of it? So let's see how you deploy Apache Pinot in Kubernetes. So in their official documentation, Apache Pinot referred to the Helm chart in their official GitHub repo. And let's see what happens when you install the Helm chart with the out-of-the-box settings. You can see that we get two load balancer services, one for the controller that we just talked about, and one for the broker, which is a component that handles the queries. That's the section from the Helm chart that is in charge for this exposure. And as you can see, if you don't explicitly disable it, the Helm chart will deploy a load balancer service. And the interesting part is that there are no default authentication mechanisms. So if you use the official Helm chart with default configuration and you don't override it, you simply open your data store to everyone in the internet. Here you can see the controller dashboard. You can control the application, you can query the data, you can do basically whatever you want. And that's exactly the pattern that we discussed about earlier. Exposure to the internet plus weak or non-existing authentication. So what can we learn from this first case? So first, default misconfigurations are still a thing. Still, there are popular applications that come severely insecure by default. And second, detecting those issues at scale is sometimes hard. Understanding configuration of each and every workload is difficult. When you manage hundreds of applications across multiple clusters, it's really challenging to really identify such cases when they occur. Okay, so at this point, we had to choose. We could either write a blog post about the finding or go down the rabbit hole and start digging through more Helm charts on GitHub. And you can probably understand what we decided. Yeah, so we decided to look for exploitable misconfigurations in large scale. So we scanned both GitHub and Artifact Hub, looking through YAMLs, Helm charts, and anything else that might expose services. We searched for manifests that use load balancer or node port. Then we sorted the result by popularity to prioritize the ones that really matter in the wild. And finally, we deployed the most interesting workloads in a test cluster to check the exploitability. So first, we took the naive approach. We just started to look for YAMLs that expose load balancers in GitHub code search. This isn't enough, of course, because you cannot really sort the results based on the number of stars and popularity. So we couldn't understand what's interesting and what is not. Then we tried to apply some more filters. We searched specifically for the values file of Helm charts. We also filtered some noisy patterns like test and tutorial environments, but still, we were limited. GitHub code search shows only up to 1,000 results, and there are much more potential repositories. So we decided to write a script that split the GitHub queries to small chunks. For example, one thing that we did was split the queries based on the port numbers. So we searched for load balancers with port numbers that start with 1, then port numbers that start with 2, and so on. And in that way, we could collect much more results. Then we sorted the results based on the number of stars to identify the interesting repos that are actually popular. So here are the results. So that's what we did. We scanned more than 12,000 Helm charts in almost 7,000 unique repositories. We then deployed and tested more than 300 popular applications that received at least 500 stars. And here are some key insights. So the first thing is that we still see popular applications with hard-coded default credentials. If they are not, if they are not explicitly modified, they go all the way to production. Some applications still come out of the box without any authentication mechanism at all, like we saw before, even a simple one. And some applications allow self-registration. We're going to see an example shortly. Now, those are some severe misconfigurations that come out of the box. Now, real-world data shows that users rely heavily on default configurations. So it makes this issue so dangerous. OK, so now let's deep dive into two examples that we found. We'll start with Meshery. Meshery is an open source tool that lets users visually design cloud-native applications. With Meshery, you get a cool drag-and-drop interface that lets you create template of resources, share it with others, and deploy it on your cluster. And also, you can deploy services from cloud providers and integrate it there. So deploying Meshery in Kubernetes, it means that you can manage the resources in the cluster. So for installation, Meshery's documentation refers to the Helm chart they created. And our GitHub scanner noticed that the Meshery application is exposed by default with a load balancer and could be accessed from outside the cluster. So when you access to the external IP address, you reach to this login page. So far, it seems OK. Maybe default internet exposure is not ideal, especially not for management interfaces, but at least we have authentication. The thing is that by default, when you press sign up, you can simply create a new user and then log into the application. And when you log in, you are greeted by this dashboard that contains all the information about the cluster and the deployed applications. And when we navigate to the drag-and-drop interface, we can deploy a new container in the cluster. So here we created a pod that shared the PID and network namespaces with the host. And when we click deploy, a new pod is running in the cluster with our configuration. Here you can see the permissions of the application. So not surprisingly, Meshery has cluster admin privileges. So once you get access to the dashboard, you can do essentially anything in the cluster. You can also deploy Meshery by using CLI that they provide, in addition to the Helm chart that we saw. Also, with the CLI, we see the same issue, and the application is exposed by default to the internet and allows registration. So to summarize, gaining access to the Meshery dashboard gives you effectively cluster admin permissions. And depends on the application on the cluster, it might also allow lateral movement to different workloads. OK, another example is Prometheus and Grafana. I guess that you're all familiar with both of them. So Prometheus is an open source monitoring system that collects and stores metrics. It gathers data from different sources and stores it in time series database. And Grafana turns this data into real-time interactive dashboards. So Prometheus does the collecting, and Grafana makes it human-friendly. So while we looked at the results from the GitHub scanner, we came across an interesting chart. This Helm chart under the Prometheus community repo deploys Grafana and Prometheus. And when we deployed it, it seemed like the password to the Grafana dashboard is stored inside the Kubernetes secret. And when we looked at the Kubernetes secret, we were surprised to see that it seems like the password to Grafana isn't such a big secret. You can see here the hard-coded password. And as expected, the out-of-the-box configuration in the values file of the Helm chart included the hard-coded secret. You can see here, prom operator. Actually, there is already a pull request to fix it, just sitting there, waiting to be merged. So by searching on Shodan, we can find tens of thousands of exposed Prometheus and Grafana instances. By design, Prometheus assumes it's running in a trusted internal network, so it does not require authentication by default. Grafana does require a password by default, but even if only a very small portion of the instances are misconfigured, it's still thousands of exposed services. Okay. So we talked about default misconfigurations, and we talked about the scanner we developed. And now, like any other session probably in KubeCon, we are going to talk about AI. So first, it's already clear that Kubernetes became the underlying compute of AI applications. We see it in real-world data, and we can also see it here in this survey by CNCF. And so at the beginning of the presentation, we talked about the early days of Kubernetes, if you remember, in which security wasn't always the first priority. And in AI applications, we actually see a quite similar pattern. Organizations are in a race to implement and integrate AI solutions. And that speed often comes at the expense of security. It's just faster to integrate AI applications without thinking too much about security. And we are going to see some examples. So first, MCP servers. So MCP, probably many of you are familiar with it. MCP is a protocol that allows AI agent to discover and invoke tools, which can provide access to external data sources or capabilities. You can run MCP servers locally or remotely. And we see many MCP servers that are running in Kubernetes. MCP supports authorization. It supports overflow. So tools can be invoked securely in the context of the user, but MCP does not enforce it. And wrong implementation of MCP servers, especially remote MCP servers, can lead to severe consequences. If the MCP server has access to sensitive information and isn't properly designed, users can remotely access to that server and invoke the tools. And here are some things that we saw. Remote MCP servers without authorization that seem to expose data from ticketing systems, HR data, and also private code repositories. And in general, we see a large number of containerized AI applications which are deployed in a misconfigured way. It's not always a default misconfiguration. Sometimes users just skip basic security principles simply for convenience, like we said, to get things deployed fast or avoid dealing with some complex setups. And let's see a few examples that we see in the wild, things that we actually see. So we have seen exposed MLflow instances. This allows anyone to manage the MLflow workload, including exfiltrate data, upload malicious models, and more. We have seen users that expose Mage.ai instances, which is a data pipeline platform. As you can see in the screenshot, Mage.ai allows you to run shell, actually, inside its container. And this container has a privileged service account mounted to it. So once you have access to Mage.ai, you basically cluster admin. Up until recently, the Helm installation of Mage.ai exposed the application by default to the internet without authentication. And after we reported the issue, they immediately added authentication by default, which is better. Another example is K-Agent, which is a platform for building AI agent Kubernetes that automate cloud-native tasks. By default, K-Agent is accessible only internally, which is good. But we see cases in which users manually expose K-Agent externally to the internet for convenience. Since the out-of-the-box installation of K-Agent doesn't come with authentication, exposing K-Agent to the internet means cluster takeover and potentially also lateral movement. In such cases, attackers can also steal the API keys that are used by K-Agent to connect to the AI services like OpenAI or Azure Foundry. Another example that we saw is NVIDIA RAG blueprint deployments, which were observed exposed to the internet, as well as Google ADK Assistant instances. So these are just few examples of misconfigurations we actually see in the wild, and this demonstrates how sometimes in the race to implement AI in the organization, security is just left behind. Okay. So now let's talk about statistics of what we saw. So we performed a large-scale analysis of thousands of Kubernetes clusters, and that's what we saw. 40% of the clusters has at least one external-facing load balancer. 20% of the clusters are exposed by a Helm chart that creates a new load balancer. And 3.5% of the exposed applications also have a privileged service account attached to them. Those are maybe the most critical workloads. Now, the fact that they're exposed does not mean that they're misconfigured. Yeah, it could be fine. But in case of a misconfiguration, they can lead to cluster takeover. So let's talk about mitigations and detections. As we said, before, exploitable misconfigurations are usually a combination of internet exposure and weak authentication. Let's begin with the internet exposure. We should always map the external surface of our organization. Obviously, some applications should be internet-facing, and it's by design, and it's fine. But sometimes this exposure is actually a misconfiguration. And there is an interesting pattern that we see over and over. Users manually change the service configuration from cluster IP to load balancer, often for debugging and testing purposes, and just keep it as is. You can identify such cases by monitoring the Kubernetes audit log and see when users change the service configuration. And if someone changed the service type from cluster IP to load balancer, it's something that you want to check, at least to check. Now, let's talk about authentication. In cloud-native applications, this is often configured in the application manifests. So look for problematic settings like allowing anonymous access, and also look for usage of default credentials or easy-to-guess ones. And here are some community tools that can help us to harden the cluster and prevent those risks. First, Kyverno and OPA, Open Policy Agent, both allow you to author policies to get deployment to the cluster. You can use them to prevent deployments of such misconfigurations like we saw. And then we have kubelinter, which you can integrate to your CI/CD pipeline to identify misconfigurations and risky configuration before they are deployed to the cluster. And Trufflehog, which is also a useful tool that can identify secrets in your YAMLs. You can also integrate it to the CI/CD pipeline to identify secrets before they reach to the cluster. Here's an example from Trufflehog, which identifies secrets. And another example is applying policy to restrict creation of load balancers. This example is from Kyverno. OK, so as we said, it's difficult always to identify the exploitation of such misconfiguration. And it's difficult to have a generic rule that can identify such exploitations. But still, we have noticed something interesting. So many containers have predictable activity, and it's not new, and it's not surprising. Containers usually run a single application and therefore behaves quite consistent over time. But turns out that most of them are very consistent. Our large-scale analysis showed that by average, containers are running 4.5 different processes, and less than 1% of the containers are running new process after their initial bootstrap. So by tracking the behavior of containers, for example, by using eBPF tools, we can try to identify anomalies in the container's activity and potentially identify exploitation of misconfigurations. And here are some known open source projects that can help us to do it. Tracy from Aqua, Falco from Sysdig, Tetragon, and Spectral Gadget. Here is an example of Inspector Gadget. You can use it to track the running processes in the container to find such anomalies. And And you can also use inspector gadget to monitor the DNS query to the containers. So in the bottom half, we see a container that accesses mining pool. For this demonstration, it's just by using NSLOOKUP. And in the upper window, you can see that you can see the actual DNS request in the gadget that shows this activity. As we just said, many containers are very consistent. So for many of them, any abnormal or unusual activity should raise a flag. OK, so let's start to wrap up what we have seen today. First, while cloud-native security definitely improved over the years, we can still find quite many issues, including popular applications. Second, what we see in real-world data is that this issue affects organizations in all sizes, from small companies to large enterprises. Everyone gets exploited by misconfigurations. As we have seen throughout the session, in some cases, the misconfigurations come out of the box. It's not even about a mistake that somebody does. Sometimes it's just relying on the default settings. And that's why it's crucial to really understand what we deploy and not just trusting the default configurations that come out of the box. We have seen cases in which misconfigurations were exploited in less than 10 minutes from the deployment. So that makes it so dangerous because the exploitations could be so fast. And lastly, more than 50% of the attacks that we see against containerized applications originate in misconfigurations and not software vulnerabilities. So even if your organization has the best vulnerability scanner with 100% coverage, and even if you automatically block vulnerable applications, still, you only did half of the job, because misconfigurations are actually in charge of more than 50% of the exploitations, of the active exploitations. OK, so we saw the default misconfigurations still happen in 2025. And I hope that the session gave you some insights about this problem and hopefully also some tools to mitigate the risk. Thank you very much. I'll be down here to take questions and talk to you. Thank you.